Welcome to our 9th learning workshop. This is going to be over the periodic table, or rather, it's going to be over electron configuration and quantum theory. So to start, I want to note that there's a lot of different facets of quantum theory. You'll probably have seen some of the equations, like for example, that the speed of light c is equal to h, or rather, it's equal to lambda, which is the wavelength, times nu, which is the frequency. And that cursive looking v is actually the Greek letter nu, and it's for frequency. So speed of light is equal to lambda times nu, frequency times wavelength. You'll also see that the energy of a particular photon of light is equal to h times nu. So the energy is dependent upon the frequency. The higher the frequency, the greater the energy. C and h are both constants here. So C would be like roughly about 3.00 times 10 to the 8th meters per second. And h is going to be 6.626 times 10 to the negative 34th joules second. So joules per second. Or actually, no, not joules per second. It's actually joules times seconds. My bad. Let me erase that. There we go. So it's 6.626 times 10 to the negative 34 joules times seconds. Okay. So those are two constants. And then, of course, the frequency and the wavelength. Those are things that we can determine by measuring the light that we're studying. Now, in truth, I don't want to actually spend a tremendous amount of time with this because honestly, most of this is pretty straightforward. It's pretty much straight up plug and chug type stuff, and it's things that you can kind of figure out. The only thing that I'll say about this is watch your units, because a lot of times they give you like a wavelength. They'll give it to you in nanometers. They might say, well, it's 420 nanometers is the wavelength. Well, one thing you should notice about this particular wavelength is nanometers does not match with meters. And joules, this is another important idea, another thing that you should note. Joules actually is a complex unit. It's actually kilograms times meters squared per second squared. So kilogram meter squared per second squared. Note in each of these cases, it's meters. So if you ever get wavelength, that means you're going to have to convert the wavelength to meters if it's not already in meters. Otherwise, it's not going to match the units and you will not get the right answer. But what I want to focus on tonight primarily is really going through electron configuration, helping you to understand what electron configuration means, and also going through orbital notation and helping you to understand the relationship between quantum numbers and electron configuration and orbital notation, because they are all connected. So at this point, I'm going to go jump down to the periodic table of electron configuration. So this periodic table is set up to show the periodic table as a roadmap for electron configuration. So the periodic table is a roadmap for electron configuration. It shows you in what order electrons will fill around the nucleus. Now, as you're probably already familiar with some of these models of electrons, I'm going to kind of show you in sort of a diagram fashion what this is actually kind of telling us. So let's take, for example, an element like aluminum, okay? So if I take aluminum as an example, this is how the electron configuration for aluminum would work. I read the periodic table just like I would a book. I start at the top left and I go left to right, and then I go down to the next row, and then I go left to right, and then I go down to the next row. Now, when I say read it like a book, I'm assuming like, English or Western languages. I know that Arabic is different and Chinese is different, but in most Western languages, it's left to right. So anyway, um, if you start with the top left like this, the first one that's going to fill up is the first energy level that's going to fill up is the first energy level. The first energy level represents, so if this is my nucleus, the protons, neutrons, and electrons, the first energy level represents the area that's closest to the nucleus. And the S block, remember, S orbitals are shaped like spheres. So they have a spherical orbit. So S can stand for sphere, if you like. These are spherical orbitals. In other words, the electrons are going to travel in a spherical orbital. So in the first energy level, I can only have an S orbital. And each box on the periodic table represents a place for one electron. So this represents a place for one electron, and this represents a place for one electron. There are 2 electrons that can add to the first row. So I'm going to go ahead and I'm going to add those 2 electrons to my first energy level. So here's 1 and here's 2. I've made the electrons yellow here. Okay, so now after that I go across. There's nothing else that can add in the first energy level, the first shell. So then I go to shell number 2, the second energy level. Once again, it's the S orbital that fills first. So the second energy level refers to the distance from the nucleus. So the second energy level is farther away from the nucleus than the first energy level. And there are 2 electrons, or there are 2 places for electrons to inhabit. Each box represents a place for one electron. So in that second energy level, that second orbital, I can have 2 electrons. So I'm going to put one here, and I'm going to put one here. Okay. After that, if I go across, I see that I have a p orbital. And this is still in the second energy level, so this is 2p. Now p orbitals are shaped kind of like a peanut. Okay? And some people say they're shaped like a dumbbell, and some people say they're shaped like other things. But I like to use peanut because it does kind of look like a peanut, and P is the first letter of peanut, so it helps you remember. P for peanut. The p orbitals are peanut shaped. And then, so I'm going to color my p orbitals a different color. They're going to be orange. The p orbitals extend out about the same amount as the s orbital. It's the second energy level, so they're going to extend out about the same. And then so it goes up and down, left, right, and in, out. Okay? Up and down, left, right, in, out. There's 3 p orbitals in the second energy level. Each one of those orbitals, each one of those pathways can hold 2 electrons. So I'm going to put 2 electrons in each one of those pathways. 1, 2, 3, 4, 5, 6. So in the electron configuration, I've already done 1s2. I put the first spherical orbital. Then I went a little further out, and it goes 2s, and then I indicate the number of electrons with the superscript, so it'll be 2s2. And then for this, there's 3 p orbitals, but they're all part of what's referred to the same subshell. And so it's going to be 2p6. 2p6. So there's 1s2, 2s2, 2p6. Okay? Because each one of these boxes represents a place for one electron. And effectively, The p subshell has three. The p subshell has three orbitals, each of which can hold 2 electrons. All right, I still haven't arrived at aluminum yet, so I'm going to keep filling up boxes until I get to aluminum. So I'm now in the 3rd energy level. What orbital is going to come next? What do you think?
It should be S.
Yeah, it's going to be a 3s. So the 3s, it's going to be, once again, it's going to be spherical just like the other times, but this one's going to be even further out. And how many electrons can enter the s orbital?
3.
Not 3. Each orbital can only hold 2, right? There's only 2 places, 2 spaces. Does that make sense? Each box represents a place for 1 electron. So it can only hold 2. Does that make sense?
Yeah.
Okay. So I'm going to put an electron here, an electron here, and then I have the p block. And I only need to fill up one more, I only need to put one more electron because I only have 13 electrons. I only have 13 electrons, and aluminum is my last one. I only have 13 electrons, aluminum is my last guy here. So I will go ahead and just, I can draw all my 3p orbitals. 1. Sorry, my drawing is kind of terrible. And then all right, so there you go.
What do you think about simplifying this this shape by just using energy levels, kind of like, you know,
I mean, that's all fine. That's all fine and good, but there is a reason why I'm showing it, and I will I will show this more simplistic method as well. But I want them to understand what is implied behind this. What is implied behind this? These numbers and letters. So this is like you said, we did the 3s2. And we only needed 1 electron. So I'll put the 1 electron we have right here in that one of those 3p orbitals. So this is this complex craziness. That's what's going on inside an aluminum atom. And these electrons are spinning around at blinding speeds. In fact, if I recall correctly, the speed of an electron is, generally speaking, somewhere in the order of magnitude of 10 to the 6th meters per second. To give an idea how fast that is, it's about 1/100th the speed of light. That's really, really wicked fast. So these electrons are moving around at blinding speeds. Okay, and I'm going to show my age here, but has anybody ever seen, have any of y'all seen the original X-Men movie with Patrick Stewart as
I have.
Professor?
Yes.
Yeah.
So do you remember the scene where Magneto like starts having, or actually I think this might have been like the second one, but Magneto breaks out of the glass prison and he has that metal ball that he has spinning around him really fast.
Yeah.
Yeah, think of those as like electrons around the nucleus, okay? Except that instead of going around, think of the speeds at which that metal ball is spinning around Magneto as being really slow compared to what an actual electron is. So these electrons are spinning around so incredibly fast, it effectively creates sort of like a force field through which there is no penetration, or at least it's really hard to penetrate. So you might ask yourself, if atoms are mostly empty space, then why can't when I put my one hand against another hand, why doesn't my hand just kind of phase through? They're mostly empty space. You'd expect your hand to simply just phase through, like just pass right through. The answer comes in the fact that the electrons create a force field. It's basically the electrons on the outer surface of the atoms of one hand repel the electrons on the outer surface of the atoms in the other hand. So you can't actually push your hands through one another. And if you rub your hands together, you end up getting a sort of friction between them because it's the scraping together of those electric fields, so to speak. And some electrons are sometimes ripped off, but there's more than one electron on your aluminum, so there's a lot of electrons to penetrate to get to the nucleus. And that's why we can't put our hands through solid objects. They're solid because the electrons on the outer surface repel electrons of anything trying to go through them. Does that make sense?
It makes sense to me.
I realize I mean, I don't know if you ever really thought about it, but it's actually really kind of cool to understand, how that translates into real life. Okay, now you should notice after putting that last electron in the 3p subshell, because this is a 3, and it's going to be in a p, so this is going to be 3p1. So effectively, what this electron configuration tells me, electron configuration of aluminum, what this tells me is where are the electrons sitting in an atom? Where are the electrons sitting in an atom? Okay? So what I would like to, I'm going to go ahead and do another one that's a little bit more complicated. And I'm going to do another one that's not too much more complicated, but I'm going to have you do it with me this time. I'm going to erase all my little markings here. So let's do, actually, let's just do simple one. Let's do oxygen. Let me have you guys do it with me. So if we're going to do the electron configuration for oxygen, where would we start?
1s2.
Exactly, 1s2 is going to be the first one. And then what comes after 1s2?
2s2.
2s2. And after that?
I guess 2p3.
2p3.
Or 2p4.
2p4. You're going to go all the way to oxygen.
You go to it. So then why did we not? Oh, we did. Never mind. Don't listen to me.
Yeah. So 1s2, 2s2, 2p4. Okay. So let's go ahead and skip ahead and let's do 26. Let's do iron.
Can we take a step back for a second?
Sure.
Just want to make sure I'm getting the subscript that you're writing on the right side. So you go from left to right and from high to low, and each box, so each square contains one, represents one electron.
Each square represents a place for one electron. Exactly.
Okay. And so it stops at 1s2 because there's nothing else in the first row.
Exactly.
And 2s2 because there's only 2 in the second row. On the left side of the second row.
Yeah, the s orbital can only hold 2 electrons, and after the s, you have to go over to the p. But there is a 2p. Exactly.
Okay. So the p orbital can hold 1, 2, 3, 4, 5, 6.
6.
Okay.
And it's a p subshell because, strictly speaking, orbital is one pathway. And the p block, actually has three different pathways, three orbitals. You can think of like three orientations of a peanut. You can have it going up and down. You can tilt it on its side and have it going side side, or you can tilt it away from you, and or so that it's pointing away from you, and then it's an in out. So there's three different orientations of the p orbital. It can be up, down, side, side, or in, out. And each one of those orientations, each one of those pathways can have two electrons traveling on it. And that gives you a total of 6 different pathways. I mean, 6 different total electrons in the p block.
What's the difference between an orbital and a shell?
Okay, so a shell represents the entire energy level. So everything in the second energy level is the second shell. So the 2s and the 2p orbitals, all of the 2s orbitals and all the 2p orbitals, all the orbitals that have a 2 in front of them, they're part of the second shell. The second, because when remember how I mentioned how the electrons are spinning around the nucleus really fast? And so you can think of kind of like a force field. You can also think of it kind of like a shell or coating. So there's the first shell, the first coating, and outside of it there's a second shell, a second coating, or second surrounding of electrons that are protecting that nucleus. And if there's a third shell, it's a third group of electrons that are spinning around the nucleus, creating a third layer of protection, so to speak. So you can think of the shells almost as layers of protection for the nucleus.
Another way of describing the shell is that the shell is a collection of orbitals with the same value of n being the principal quantum number, as opposed to an orbital. An orbital is really, it's a wave function, and we won't get into it, but just to give you an idea, is the square of this function gives the probability density for the electron. So the difference is that an orbital, each orbital has a characteristic energy and shape, and a shell is a collection of orbitals with the same principal quantum number. I hope that helps.
Yeah, it's basically all orbitals that are roughly the same distance away from the nucleus. So yeah, so Dr. Neely is giving you the precise terminology, which is good, which is valuable. Admittedly, I'm kind of I hate to use this word because you're not dumb, but I hate to I'm trying to kind of dumb it down, make it more understandable. I think I should just say make it more understandable. I'm trying to make it more understandable by putting into common wording, because otherwise it's kind of confusing.
Yes, Professor DePaul has the prowess to put it in pedagogical terms. Thank you.
Thank you. Yeah, so now a subshell is a group of orbitals with a particular shape in a particular energy level. So like, for example, the 2p subshell is those three orbitals, those three peanut-shaped orbitals that are in the second energy level. So within every shell, there's also subshells. And the subshell refers to all the orbitals of a particular shape. Does that make sense?
Subshell refers to orbitals in a particular shape.
Of a particular shape. So like the second energy level has two different types of orbitals. It has s orbitals, which are spherical, and p orbitals, which are peanut-shaped. The second shell contains 4 total orbitals, 1s and 3p. The 2p subshell refers to only those orbitals that are peanut-shaped, only those orbitals that are p orbitals in the second shell. Does that make sense?
Yeah.
Yeah, it's kind of like a sub-classification. You're breaking down the shell into smaller pieces. Okay, so now that we've got that out of the way, let's go ahead and tackle E. Let's go ahead and tackle Fe. So let's go ahead and look at what the orbital, what the electron configuration of iron would be. Okay, so for iron, what would I start with? Here's iron, by the way.
1s2.
Yep. Notice how it always starts out the same way. What
Then
comes next?
2s2.
2s2.
Then 2p6.
2p6. And what comes after that?
3s2.
3s2. What comes after that?
3p6.
Very good. 3p6. We've boldly gone where no one has gone before, or at least we haven't. So what's next? We still haven't gotten to iron. 4s2. And then, what comes after that?
4d6.
And so I kind of tricked you. Ethan knows that I'm kind of terrible for doing this, but I always like to set you guys up to make mistakes. In the D block, it turns out that you end up having to drop an energy level. So when you go from, it looks like it's in the 4th energy level, but when you cross into the D block, it actually drops an energy level. So this whole group is actually a 3. So this is not a 4D, but this is actually 3D.
Oh, okay.
And so you say this is 3D what?
6.
3D6. And the reason that that's the case, if I go over to my drawing, my diagram here of aluminum, I'm going to go ahead and erase these guys up here because I want to show you something kind of cool. So here's my diagram of aluminum. Let's say it wasn't actually aluminum, but let's say it was like scandium or titanium, okay? Which means that I'm going to go ahead and I'm going to put 2 electrons in each of those 3p orbitals. As you can see, it's already getting pretty convoluted at this point, right? It's already getting pretty messy. Well, after the 3p6, I have a choice. After the 3p6, I have a choice. I could either go to the 4D or the 4s, basically just kind of go around it, or I'll choose a different color, do light blue, or I could do this complex pathway in the 3rd energy level. It kind of looks like this, kind of weaving between and around the other electrons. Which do you think is going to be easier? Which do you think is going to be lower energy? An electron shooting around through that very complex pathway, or going around in a simpler pathway?
I think going around in the simpler pathway, but
Yeah, going around in the simpler pathway is going to be easier. So this is why you get a 4s2. This is why you get a 4s2 before you get any 3D. So like if this was scandium, I might put a 3D now in, because after the 4s2 is filled up, the other option would be 4p. Well, with the 4p, once again, I'm dealing with all this other mess, plus I'm moving in a more complex pathway, plus I'm further away. So all those factors make 4p definitely not favored. A 3D is going to be better than a 4p. But 4s and 3D are very close in energy, and it turns out that 4s is actually a little bit lower than 3D. And this is kind of why. So that's what I wanted to show you with my ridiculous drawing.
Are we gonna need to know how to draw that too?
No, no. But I do want to actually draw an energy diagram somewhat similar to the one that Professor Neely drew. Energy as it's going upwards here. So if I was to write out the energy levels of these different orbitals, so here's, okay, this would be like, say, a 1s, here's a 2s, here's a 3s, here's a 4s, here's a 5s. Okay, so I'm going to label these 1s, 2s, 3s, and each one of these lines represents an orbital, okay? And you may actually be expected to fill out some of these orbital diagrams, because I have seen this in the homework before. Now, you also have the p orbital, and the p orbital doesn't show up until about the second energy level, but the p orbital, it's a bit higher in energy than the 2s. And you'll see that it has 3 orbitals. So this is your 3 2p's. Okay, and so basically this is your 2p, your 3p, and your 4p. Well then, let's see, I'll do the D. Now D doesn't approach until you get here, but here's our D after 3p. Get 1, 2, 3, 4, 5 3D orbitals. Okay. And then likewise, the 4D would be 1, 2, 3, 4, 5D. 5D orbital. So this is the 3D, and this is the 4D. Now you'll notice that the D, if you line it up along with the S, you see the D is just a little bit higher in energy. The 3D is just a little bit higher in energy than the 4S. So the 4S actually gets filled first, and then the 3D. And likewise, the 5S is just a little bit lower in energy than the 4D. So the 5S is going to fill first, and then the 4D. So whenever you drop into go into the D block, you drop an energy level in the periodic table, but that's simply because the energy of the system, these electrons are just trying to go into the lowest energy orbital possible. And the periodic table was arranged by common properties, but it turns out that the reason why there's these common properties is because they have similar electron arrangements. Okay, they have similar electron arrangements. Does that make sense?
So far, yeah.
Okay, cool. All right. So what I've just drawn you here is what can sometimes be called an orbital diagram. Okay, and sometimes orbital diagrams are complex like this, and sometimes orbital diagrams are going to be simpler. But before I get too far into orbital diagrams, there's one other thing that I want to do. And I'm going to go ahead and erase my ridiculous drawing over here. Okay, that's really, sorry.
Yes, I was going to say, please erase that too.
Sorry, I feel terribly rude erasing
No,
it.
yours is a lot prettier. I like yours more.
Okay, well, thank you. So now let's say, for example, we were to do the electron configuration of something like lead. Before I jump into orbital diagrams, I want to teach you a little shortcut. But before I do, I want to help you realize how painful it can be. So, shame on me. So let's do lead. Let's do the electron configuration for lead. Here it is. You tell me what to write, and I'll correct you if you make a mistake, but I think you guys got this. Start from the very beginning. As Fräulein Maria would say, a very good place to start.
One
Sorry.
S2.
1s2. I got no chuckles. Nobody's watched The Sound of Music. A classic, guys. All right, what comes after 1s2?
Ethan's audio is out, but he liked it. And
Oh, okay.
and I hate to say it, but I didn't catch the joke, and I'm embarrassed to ask.
Oh no, it's okay. Basically, in the movie The Sound of Music, she's teaching the kids how to sing, and she goes, "Let's start at the very beginning. A very good place to start." And then, so yeah. So let's start at the beginning. It's a very good place to start. So anyway, yeah. So now you got me singing. Shame on me. All right. So what comes after 1s2?
Ethan said 2s2.
2s2. Good. And what comes after 2s2?
2p6.
2p6. And after 2p6?
3s2.
3s2. Very good. Good job. And after 3s2?
3p6.
3p6. Next,
4s2.
4s2. And then
3d 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
Ethan, you were
3d10. Very good.
You were very close, Ethan. You get 90%.
And I'm going to grab my little hand here. I need to, oh wait, whoops, what am I doing? I need to, there we go. I need to pull my screen over. There we go. Now I can continue. After 3d10, 4p6, I think is what Ethan said.
And then 5s2.
5s2. And then after 5s2,
Wait, which one are we going to? Lead? Okay.
lead, number 82. We ain't done by a long shot. After 5s2,
4d10.
4d10. And after 4d10,
5p6.
5p6. You're doing it, you're doing it. Okay, what comes after 5p6?
6s2.
6s2, very good. Now this is where it gets just slightly tricky. What comes after 6s2? Here's your 6s2. Note the number though. That number is what?
The next number?
Well,
71?
this is 50, after 6s2 is 56. Where's 57?
Great question. Oh, it's all the way at the bottom in F.
Yeah, it turns out that they were lazy when they made, well, they weren't lazy. They did this for space reasons, but the periodic table, that bottom section is actually supposed to be in between the 56 and 71. You have to cut the periodic table right along that line and split the yellow and blue parts and stick the green in the middle between them. That's the way the periodic table should look, I guess, quote unquote. But unfortunately, it wouldn't fit on one piece of paper very nicely with decent enough size lettering. So instead, they pulled it out and put it down. So what that means is that when you do periodic configuration or electron configuration, you have to go from here to here. And notice what it says about the F block.
Drop 2 energy levels.
So what energy level would this be?
4.
4. And how many electrons would fill up in the fourth energy level? The 4F.
14.
14. So after 6s2, it's 4f14. But After that, then
You
we
go
can
back
go
to
back. After 70, we can go back here and go up to 71. So that's going to be what?
5D10.
Mm-hmm. 5d10. And then after 5d10,
6P2.
6p2. Very good.
Ethan's funny.
so, so that's a
That was
pain
a
in the
lot.
behind.
Yeah, that was a lot.
But there is an easier way. It's called condensed electron configuration. You don't have to write out that whole monstrosity. Instead, you can go from the previous noble gas. So this is called condensed electron configuration or noble gas notation. So let's write the electron configuration of lead with noble gas notation. What you do for noble gas notation is you simply start from the previous noble gas. What noble gas comes before lead? Remember, these are your noble gases right here.
Xenon.
Yeah, xenon. So what I do is I'll put a bracket Xe, and if you want to, it's optional. You can put the number of electrons filled up to that point. That Xe54 basically takes care of all the, the 1s2, 2s2, 2p6, 3s2, blah, 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 until you get to the xenon. Then you go straight to what comes after. What comes after xenon? What orbital fills next?
6.
Yeah, the 6s2. And then after the 6s2,
5D10.
oh, not 5D. Look at the arrows. Look at the numbers.
Oh. 4F14.
Yeah, 4F14, and then
5D10.
5D10. And then after that,
Ethan, you gotta take over. I gotta write some notes.
and then after that,
It's going to be
6p2.
6p2.
Yeah. So basically, noble gas configuration saves you a lot of time.
So why could we not apply a similar concept and just do thallium and then add 1?
I don't know, because thallium is not a very well-known marker. And also, the emphasis is on the valence electrons. You bring up a good point, but the emphasis is on the valence electrons, because the valence electrons, the outermost electrons, the highest energy electrons, if you will, those are the ones that are involved in bonding. Those are the ones that are involved in chemical reactions. And those are the ones that help to determine the properties of an element. So when I write out the highest energy level electrons here, that's what the noble gas configuration does. Anything that's the noble gas or the previous noble gas or below is an inner shell electron. And so it's not going to really be involved in any chemical reactions or things like that. I mean, not generally. And so the reason why we do the condensed configuration, because it still tells us the most important electrons. And the most important electrons are the ones that are involved in bonding. Does that make sense?
Yes, it does.
So,
Why is this helpful? Like, what is this used for?
it helps us to understand why we get certain ions. It also helps us to understand why things behave the way they do if we understand where these electrons are coming from.
It also helps us understand ionization energy processes and electron affinity processes. So it's very fundamental, very important.
Admittedly, if you're a doctor or if, I mean, like if you're a medical doctor or something like that, this is probably really never going to come into any use for you. It's not going to be useful. If you're a materials chemist, or if you're a physical chemist or a materials chemist and you're dealing with the theory or you're dealing with developing new things, then this actually really could be useful to you.
Okay. I hope that didn't come off as like a smart aleck comment. I genuinely
No,
wanted to
no,
know.
it's not. No, I mean it's a very valid question. I mean, what's the point of it? Like, I mean, seriously, why do we bother with this? Now, I will say this: there is a certain sense in which knowledge is valuable for its own sake. Like, understanding things is meaningful and worthwhile simply because understanding itself is meaningful and worthwhile. But that said, I also understand you'd be like, well, what's it good for? I mean, we always tend to think of things in terms of their practical uses, but some things are worth learning and worth understanding simply because it is worth your time to try to understand the nature of the universe in which you live. You know what I'm saying? And I don't mean that to be like in any way diminutive of your question. Your question is a very valid one and a very valuable one because when you discover new things about nature, atoms, molecules, etc., the question, well, what can I use this for? What is this good for? What could I potentially use this for? Is one in which most scientists are really interested in. They want to know, well, yeah, what is this good for? I want to see if there's something I can do with this that might be, cool or useful or contribute to the betterment of mankind. So that's a
Actually,
long answer. All right, so jumping forward into the next topic, I know that's kind of an abrupt segue, but um, from here you can actually do what's called an orbital notation. So you already had the big orbital notation diagram that I drew on the bottom here, but there's also you can also do orbital notations for these electron configurations just in the form of this. So like, let me show you what I mean. Um, so I like to draw orbitals not necessarily as lines, but as boxes, and you can really do either one. But with lead, this one, so an S orbital or S subshell has only one orbital, so I would draw like one box. And I could actually label it even, I could draw it as labeled as a 6s. Now the 4f orbital has 14 electrons. That's because there are 7 different orbital pathways in the 4f subshell. And I draw them connected like this to indicate that they are actually of equal energy. Each one has the same energy as each other one. Now this is a 4f subshell, a 4f group of electrons. Now the 6s says 2, so I can show the electrons by actually putting the electrons as arrows. And I'm going to, in each orbital, in each box, only one electron can be up and then only one electron can be down. And then up and down represents opposite spins, opposite spin states. Okay? So if you think about it like this, in physics, and this is an imperfect analogy, and I don't want to get into too complicated science behind it, but it's still an analogy, or it's still a description that works. So when an electron is a negative charge, right? And when
Right.
a negative charge spins, it produces a magnetic field. Electrical charges and magnetic fields are intertwined. One affects the other. So when electric charge spins, it produces a magnetic field. If it spins in the opposite direction, it produces a magnetic field in the opposite direction. So electrons, electrostatically, they have the same negative charge, don't they? Two electrons in the same orbital are going to have the same charge, right?
They should.
Yeah.
Yeah, exactly. So, and if they have the same charge, are they going to repel each other or are they going to attract one another?
Repel.
Repel. But see, if they're spinning in opposite directions, that means they're generating opposite magnetic fields. If they're generating opposite magnetic fields, then that means opposite magnetic fields, do they attract or do they repel?
Attract.
They attract. So even though the charges themselves repel one another based on electrostatic force, because they're spinning in opposite directions, the magnetic fields help to stabilize them and attract them and hold them in that orbital. But you can't have them with the same spin because otherwise both the magnetic field and the charge will repel each other and they'll just fly apart.
That makes sense.
So now, as a general rule, you usually fill up one electron in each orbital before any is doubled. So with the 4f14, I would do it like this: 1, 2, 3, 4, 5, 6, 7. And then if I have to, I double up, which I do in this case because it's 14. Now, this process of only putting one electron in each orbital before doubling up is called Hund's rule. And you can think of it kind of like a party. You go to a party and let's say there's pizza and cake. Well, you're not going to take 5 pieces of pizza before anybody else gets any. That would be rude, right? So each person gets 1 piece of cake until everybody's had cake. And then if there's still cake left over, then other people can grab more cake, right?
Yeah.
Unless you're Ethan, in which case all bets are off.
Yeah, unfortunately.
No, I'm just teasing. All right, so there we go. And with the 5D, once again, it's 5D10. So 1, 2, 3, 4, 5. And 6, 7, 8, 9, 10. So each arrow represents 1 electron, and the opposite directions represent opposite spins. And now we have our 6p2. Our 6p2, p is capable, or p has 3 orbitals, 3 subshells, or I mean 3 orbitals in the subshell rather. And therefore, for the 6p2, where am I going to put the electrons? Am I going to put them both in the first orbital, or am I going to put one in each of the first 2 orbitals? What do you think?
One in each one first.
Exactly, 1 in each one. So this would be that. And now those unpaired electrons, that actually has a very important implication because when electrons are paired throughout the entire molecule, they don't interact with the magnetic field. But if you have unpaired electrons, then that metal will react with the magnetic field. So in other words, one will respond to a magnet, one will stick to a magnet, and the other one won't. You need unpaired electrons in order for it to be magnetic, or to stick to a magnet, basically. All right, so this is an orbital diagram. And so this tells you where the electrons are in the spin and everything. So now I want to get into quantum numbers because I want to connect this. I want to bring this full circle. I want to bring this full circle and connect this all for you. All right. Let's see. Can I insert? No, I can't. Y'all have that notes on quantum numbers thing that I pulled up? That I
Yes.
emailed to you? Okay. So quantum numbers are kind of like an address for an electron. And I'm actually going to go ahead and type that up. So quantum numbers Yeah. Quantum numbers represent an address for an electron. So once again, this is by way of analogy, of course, but if I have an address for an electron, there's the principal quantum number, and that has the symbol N. And what does this tell us? Well, it tells us the energy level. Or in other words, how far from the nucleus. Then there's the angular momentum quantum number. Angular momentum quantum number. And by the way, this is also sometimes referred to as the azimuthal quantum number. I'm actually going to put that azimuthal. Not too many. The symbol is L, or a cursive L. Kind of more like this. That's the angular momentum quantum number symbol. And what does it tell us? Well, if you think about angular momentum, well, what would angular momentum tell you, right? And angular momentum is going to tell you,
Torque.
well, it does, but if the electron is traveling with a particular angular momentum, that angular momentum is causing the pathway to have a particular shape. So this tells you the shape of the pathway. So in other words, the shape of the pathway, in other words, is the, so in other words, is it S, P, D, or F? Is it a sphere, peanut, daisy, or a flower? Or a fountain, rather. Sphere, peanut, daisy. The D kind of has a daisy look to it. So I was going to go ahead and erase some of my babbling earlier with the iron here. So this is I'm going to draw a D orbital. So some people say double dumbbell. Some people, say daisy. I mean, you can do whatever you want with it, but I'm going to say daisy or double dumbbell. Sphere, peanut, daisy, or double dumbbell. And then F is I mean, this is only one possible shape. This is only one possible orbital shape. It actually has a number of other ones that are really weird. But so the F block is right here, and it has this kind of like fountain-looking shape, kind of like it's spraying out in all directions. I'm just gonna call it fountain. Why? Because I don't have anything better to call it. It doesn't really look like a flower per se. Oh, it kind of looks like a flower, but I don't want to take away from my daisy, which is also a flower. I'm going to call it fountain. Okay. So the azimuthal quantum number, or angular momentum quantum number, the symbol L, tells you the shape of the pathway. So what's more on that is that there's actually specific numbers that are tied to specific numbers that are tied to specific shapes. So for example, if L is equal to 0, that's an s orbital. If L is equal to 0, that's an s orbital, always. Doesn't matter if it's 7s or 1s. If L is equal to 1, that's a p orbital. If L is equal to 2, that's a d orbital. And if L is equal to 3, that's an f orbital. And we usually don't go beyond f, although technically speaking, there is a g orbital, and there are orbitals beyond that. But we usually don't go beyond f. So that's the angular momentum quantum number. So now, the next quantum number is the magnetic quantum number. And that's given by a m subscript L. Whoa, what'd I do? Zoom out. Zoom out. Okay. M with a little subscript L. Does it let me do subscripts? No, I don't think it does.
You
know,
could
I'm just
try
gonna draw.
control comma. Sometimes that does it.
Yeah, I'm just gonna draw it by hand. I'm feeling too lazy to do anything else. So that's M sub L. And M sub L tells you, the M sub L tells you which specific orbital, in the subshell. In other words, it tells you the orientation in space. Is it, like, if you think about those p orbitals, remember how I said you can go up, down, left, right, in, out? Well, this is the magnetic quantum number tells you which one it is. Is it up, down, is it left and right, or is it in and out? This is the orientation in space. It's not just it's not just the shape, it's actual orientation. And the last quantum number is the simplest, and that's just the spin quantum number. And the spin quantum number, is essentially based, it has a symbol M with a little subscript S, and that's because it's it's related to the magnetic field generated by the spin. So this is actually going to be, it can only have two possible values, positive 1/2 or negative 1/2. And it basically tells you which way the electron is spinning, clockwise or counterclockwise. Does that make sense?
Yeah.
Oh, it makes sense to me.
Okay, so
Actually,
so now
is 1/2
ahead.
clockwise and negative 1/2 counterclockwise?
The truth is it's not really clockwise or counterclockwise. I just use that by
Oh,
analogy.
I got you. That makes
Um,
sense. Never mind.
yeah, I mean, yeah, uh, it just represents the different spins.
Yeah, I think the simplest way of describing it is if, when you take physics, you'll see it. But it's called the right hand rule, and if you just take your right hand and if your thumb is pointing up and your fingers are curling, towards you, it's like the fingers that are curling towards you. That's the electron spinning on the north-south axis that creates a magnetic field in the north direction, and then the reverse. So if you reverse your hand, your thumb will point down, and the electrons are moving or spinning in the opposite direction. So it's kind of a neat. We call it in physics the right hand rule. It's kind of neat. Yes.
Yeah. So all right. So and sadly, interestingly enough, it seems that actually the spin of an electron actually has nothing to do with actual spinning of electrons. From what I've heard, there's like new experimental information that it basically indicates that it's actually something completely different that we don't actually really know how to describe. Um, but anyway, tabling that, we're going to assume that the world in the universe makes sense and it has actually to do with spinning and the right-hand rule. Let's go ahead and take a look at an example. And I'll show you how to identify and determine what the quantum numbers are for any particular electron in a substance. So if we do the electron configuration for phosphorus, it ends up being 1s2, 2s2, 2p6, 3s2, 3p3. So this is the electron configuration. This is the electron configuration for phosphorus. And if I go ahead and I do my orbital diagram, here's 1s, here's 2s, and here's a 2p. Here's a 3s, and here's a 3p. So now I'm going to go ahead and fill up my electrons in this thing. Up, down, up, down. And with the last one, I got what? Up, up, up. Now, I want to let you know, I could just as easily have done down, 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 and it wouldn't have made any difference because whether or not you start up or whether or not you start down, it's completely a flip of the coin because they're equal energy and it doesn't matter which one comes first. Okay? But, so let's do, so this is your 1s, 2s, 2p, 3s, and 3p. So I would like to go ahead and take a look at one of these electrons and let's assign quantum numbers to it. So let's do this one. So for that electron that I've circled in that 3p subshell, what is the n value? Remember, n tells you the energy level.
3.
3. So the n value is 3. What is the L value?
It should be 1.
Should be 1 because a p orbital always has an L value of 1. Now, I didn't go through what the m sub L values are. I'm going to do that now real briefly. But m sub L tells you which specific orbital it is. Now, for an s orbital, there's only one possible value for m sub L, and that's 0. Okay? That doesn't mean there's 0 orbitals. That just means that that is the m sub L number. Okay? So 2s, this will also be 0. Now, basically, m sub L can have a value of anything from negative L to positive L. So if L is 0, then m sub L can only be 0. But if L is 1, then m sub L can be negative 1, 0, or positive 1. Here's 0, here's negative 1, 0, and positive 1. And each one of those numbers represents a different orbital. So in this particular case, for the orange circled electron, what is m sub L?
-1.
Negative 1. And what is m sub S?
0.
Well, no, m sub S only has two possible values, positive 1/2 or negative 1/2. It tells you the spin of the electron.
Oh, gotcha.
Now, in truth, you could really say either one because it's just as equally likely that it could be up or down. And even the convention up doesn't necessarily have to mean positive 1/2. But in this case, we'll just assume Doesn't have to be this way, but we'll just assume it's positive 1/2. That the up corresponds to positive 1/2. So you see, this set of 4 quantum numbers tells you the address, the exact location of that electron within the, well, not the exact location, but it tells you the location of the electron within the atom. So, for example, this is kind of like with your address, you have a state, you have a city, you have a street, and you have a street number.
That's a good darn analogy. That's the first time I see that, and I like it.
So yeah, and thank you. And so that's basically what these quantum numbers are. They're an address for an electron. They show you where the electron is. So the state is that's just the energy, the general energy level. The city tells you know what region can be found. In this case, it's going to be one of the what are the p orbitals, and the street, which specific p orbital, and then the number, what specific spin is it going to have in that specific p orbital. Does that help?
Yeah, I think that makes sense to me.
Let's do another one. Let's have you do a set of 4 quantum numbers for this guy, the 2s electron there. I'm going to have you guys do this one by yourself. What is, tell me, what is n?
It should be 0. Wait, no, don't do that.
Which one did you say we were doing?
The yellow one.
It should be
The yellow.
0. Wait, what am I doing?
It
I
should
don't
be
know if
2,
that's
right? It should be 2.
2, n is equal to 2, because it's the
That's
energy
the
level,
energy
right?
level. Yeah.
So, and then what about the L? What's the L value?
0.
Yeah, that should be 0.
Yeah, the L value is 0, because it's an s orbital, right? And then the m sub L would be
0.
This is where I got lost.
0. And then the m sub s? What's the m sub s?
How about minus 1/2?
Minus 1/2 works. So that is a possible set of 4 quantum numbers for that electron. Now, oftentimes what they'll ask you for is give a set of 4 quantum numbers for the highest energy electron in, some particular atom. Well, the highest energy electron in phosphorus would be any one of these 3, either this one, or this one, or this one, because they're all equal energy if they're in the 3p subshell. So the only thing, when it asks you for the highest energy electron, the only thing that's certain, the only thing that you have to indicate really that's going to be concrete is going to be those 2, the energy level and the subshell. Because it's completely random which orbital the first electron jumps into, and it's also because they're all equal energy, and it's completely random which spin state they're going to have, whether it's going to be positive 1/2 or negative 1/2, because those are equal energy. So if you just know the n value and the L value, then you can figure out what the other values are. Now you should of course be aware of limitations. If L is equal to 0, can you have an m sub L value of 5?
No, that wouldn't make sense.
No. Okay. Yeah. So an L is equal to 0, then m sub L has to be 0, because m sub L can only be from negative L to positive L. And notice this is actually where we actually determined that there were 3p orbitals in the subshell and 5d orbitals in a d subshell and 7 f orbitals in an f subshell. It's because we actually took measurements, careful measurements with very sensitive instruments, and measured some of the values for these quantum states. And we interpreted these quantum states once we had more information and figured out that they were related to the actual orbital or the pathway that the electron was following. So for an S, so I'll do just kind of a brief summary before we get kicked off, because it'll kick us off at 8 o'clock. Blackboard Collaborate has not been very nice lately. I think it's because they know we're leaving it for Canvas, and they're like, forget you guys, I don't love you no more.
We're leaving for Canvas right in time, in the nick of time when we're coming back to campus.
I know. So this is an S, this is a P, this is a D, and this is an F. So the L values here are 0, 1, 2, and 3. And the M sub L values refer to the specific orbitals. It can either have 0, -1, 0, and 1, or if L is 2, it can be -2, -1, 0, 1, and 2. Or if L is 3, then it can be -3, -2, -1, 0, 1, 2, and 3. Does that make sense?
How did you know how many boxes to draw for each level?
Well, I know I happen to memorize the fact that an F orbital or an F subshell always has 7, and a D subshell always has 5, a P has 3, and S is 1. It's actually not too hard to remember if you think about it, because it's just odd numbers: 1, 3, 5, and 7.
Noted.
But can you see now but you could actually figure it out if you knew what the L value was. You could actually use the M sub L values to figure out how many orbitals there are. Plus, another way to figure out how many orbitals there are is if you look back at that electron configuration for the periodic table, periodic table for electron configuration, look at the number of electrons in a particular block. Notice how many electrons, how many boxes long is a D block level. How many boxes are in a D block subshell, or in a D block
10.
going across?
And
10. That means it can hold 10 electrons. Well, if it can hold 10 electrons, that means it has how many orbitals?
5.
5, half that. And then likewise, the F block, if you count them across, it's 14. Divide that by 2, you got 7. So that's another way in case you forget. Well, I think that's probably about all we have time for. But kind of like a crash course through electron configuration and orbital notation. But since you haven't learned anything on this yet, this is going to give you a huge jump start and when you hit that kind of stuff.
Thank you.
Yeah, no problem.
Yeah, I appreciate it. Hope you guys have a great week.